Welcome to Maths with Bob. Today we're looking at the dot product with vectors in 3D. Now what is the dot product? Well, let's have a look. Okay, here it is here. This is the dot product. Now, obviously it's a multiplication of the two vectors. Yes, okay. Here it is, a dot B. Okay, that's sort of looks like a decimal place, I guess, or a decimal point, or a big decimal point. It actually indicates that you are multiplying these two vectors together in a special way. And it's called the dot product or the scalar product, sometimes called the inner product. It basically just is a number. It can be interpreted geometrically, I guess, as you can see here. I've got the geometric description here. This is this one here. This is the A dot B here. This is the, you can see it's the magnitude of A times the magnitude of B times the cosine of the angle in between them. So this is the, I guess, the geometric representation of the dot product. Okay. Some people actually say you can also look at this as like the projection of A onto B, which would be, if you like, it's like a magnitude of A cos theta times the magnitude of B. Okay, so it's like the A's contribution in the direction of B times B's magnitude. Or you can do it the other way as well. You can do it as B's contribution to A, which would be B magnitude of B cos theta onto A's direction, okay, times the magnitude of A. Okay, so you can sort of think of it like a projection, I guess, of one onto the other and multiplying them together, bits together. Obviously, it's you've got the cosine and the angle in between them. So if cosine theta gets bigger than 90, it gets negative. So this scalar can be positive or negative. Now, if you have a quick look here, obviously this part here is the magnitude of A, which is in 3 dimensions. It's just the square root of x1 squared plus y1 squared plus z1 squared, where x1, y1, and z1 are, in fact, if you like, the x direction, y direction, and z direction times the unit vectors. So this is actually a position vector A. Okay. If you like, I'll just let's have a quick look at where I, j, and k are. Well, here we have GeoGebra. I just put in the unit vectors on the coordinate axes. This is along the x1 is I, the red one. Okay, j is on the y, the green one, and blue, the actual. So when these are actually, you can see here, these are actually just unit vectors. Okay, they're orthogonal to each other. Okay, so you can just have a look here. Okay, so these are just the unit vectors. If you hadn't had much experience with vectors, basically, if you like, a position vector is made up of combinations of these. Okay, these are unit vectors. Okay. Okay, well, here we are back again. Well, there are a couple of things to note. Obviously, if the angle between them is 0, i.e. they're parallel, then A dot B is just the magnitude of A times the magnitude of B. Sometimes they say if it's A dot A, it's actually equal to A squared. Okay. Anyway, there's a few things you need to have a quick look at. Obviously, if they're perpendicular, then A dot B is actually 0. This can be quite useful. And if you want to find the angle between them, okay, you have to basically, you can see here, if you want to find the angle, you obviously need to take, well, first of all, you find cos theta, which is A dot B, that scalar number, times, well, divided by, I should say here, that the magnitude of A times the magnitude of B, or if you like, their lengths. Okay. Then you obviously have to go inverse cosine or arc cos of that particular number here. I'll do an example in a little while, just to show you how to find the angle between two vectors. Okay. All right, let's actually have a quick look. If you like, the algebraic way of finding the dot product is quite easy. It's just, you can see here, this is it here, A dot B. It's just the components multiplied together. Okay. You can just see here that A dot B is really just x1, x2 plus y1, y2 plus z1, z2. Now, If you actually want to go through the proof of this, you can actually have a quick look up here. When you multiply this out, it's a bit like a binomial expansion. You have I dot I and J dot J and K dot K are actually 1 because cos theta is actually equal to 1. They're parallel. The angle between them obviously is 0. Okay, so cos 0 is 1. That's why these things are actually just 1. Because obviously, as you probably know, it's basically the length of I times the length of I is 1 times 1, basically. Anyway, if you have the orthogonal unit vectors, you can see here the angle between them is 90 degrees, and hence the cos of 90 is 0. So just remember that it's very easy to find the algebraic product, or you could say dot product algebraically, perhaps I should say. It's just multiplying their corresponding components together, adding them up, and see what number you get to. And obviously, remember, the A dot B is a scalar. Let's have a look at an example now. Okay, here we have an example. We've got a couple of vectors, A and B. I'm going to also find the angle between them as well, just for a bit of variety. Obviously, to do that, you are obviously going to need their lengths. You can see here, I've got their lengths here. This is the length of here. You can see here that's the length of A, the length of B here, root 83 and root 29, the magnitude, if you like, or lengths of the two vectors. When you go through the dot product, you'll actually find that A dot B down here is actually, what, negative 15. Now, if it's negative, obviously it just means that the angle is bigger than 90. I'll just see if I can find, if I get this, make it a bit bigger. Okay, so here we go, negative 15. So basically, how do you get that? How do you get negative 15? Well, you can see here 2 times 7, these are the corresponding components. 3 times minus 3 and minus 4 times 5. And you can see here the end result of A dot B, the dot product is actually negative 15. Now, if you want to find the cosine, okay, you can see here, I'll just move this down here. The cosine is just down here. It's going to be negative, yes, so you'd expect the angle to be larger than 90, as you can see here, approximately 108. So you basically, to get the cosine, you basically have A dot B on the top multiplied by the length of A times the length of B. Then you have to go, obviously, inverse cosine of that particular decimal here, or fraction, okay, to get the angle, which in this case is 108 degrees. Okay, we're now going to go over to GeoGebra and have a quick look at this in 3D GeoGebra. Well, here we have 3D GeoGebra. I've got some vectors here. Well, first thing I'd like to go over is that what are the position vectors? Well, the position vector of A is this vector here, which goes a bit darker here. The position vector of B is here, and the free vector AB is this one over here. So let's actually take out some of these vectors and just leave the free vector here. Okay. All right. Okay, so we now just got A, B, and you can see here the position vector of C and D. You can see here, that's obviously C here. This is C's position vector. I'll just take that out now, and oops, take it out. And D's position vector here. Okay, I'll just take that out. Okay. Now we have two, if you like, free vectors. Now they are obviously in space. Obviously we've got one called AB and one called CD. And you can see here I've got, I can just move these around. Lots of things are happening. I've actually got, if you like, U and V. These are the free vectors. You can see here there's a change B. U's length is changing. The angle between them is also changing. CD here, if you go over here. Now, what I want to try and show you is if I start trying to make one of these vectors, let's have a look, see if we can get them to be perpendicular. Okay, obviously it's pretty tricky, but you can see here as the angle gets close to 90, the U dot V is getting close to 0. Now, if I actually make them parallel, okay, making the angle, now the angle 0, it's a bit tricky as well, but if I try and make it a bit 0, you can see basically if it's actually not 1.1 there. Okay. Anyway, it's quite hard to get it to actually equal 0, the angle between them, to make them parallel. But basically, if that's the case, if the angle is 0 between the two vectors, then obviously the u dot v is just the multiplication of the lengths. Okay, you can see it just here. Okay, so that's the dot product, okay, of the two vectors. Okay, and obviously if I increase the angle, you can see here the angle is here. If I increase it to well, let's actually go through that. Obviously if it's less than 90, it's positive, the u dot v, and obviously as I get larger, okay, you can see here 140.77 degrees, the u dot v is actually negative. Okay, this is the dot product. Now you'll see that they are in the same plane. Now well, I'm not going to go through today basically how you get the equation of the plane, but I've actually put the equation of the plane up there on the top there. This is the equation of the plane here, okay, which they are lying on. You will need the normal vector, and this is actually found usually with the cross product. If you do the cross product of those two vectors, if I just show you they are on the same plane. Okay, a bit hard to see, but there, okay. Okay, here we are. All right, so these are the two vectors. They're free vectors. Okay, a bit fast, but they're basically just vectors in space. Okay, there are the position vectors of each of the individual points. Obviously, they're attached to the origin. Okay, and you can find these vectors here quite easily, CD. And the dot product, which we're looking at today, is the important thing, and that is that basically when you are finding the dot product, you will, in fact, to get the cosine of the angle in between them, you'll need to put them on, well, they need to be on the same plane to start with. That's this purple plane here, which is, you can see here, its equation is up here. There it is, purple, that's the equation of the plane. Okay. Right, well, look, that's all is for today. I'll just thank you for watching, and hopefully this has made a bit of sense. The dot product is quite an easy thing to find, really, and it's just a matter of trying to understand what's happening. Algebraically, it's quite an easy thing to do. Okay, thank you very much for watching, and bye for now.